Hello all. Hope you are all safe in the comfort of your home. I will give a set of video lectures. In the first lecture, I will give a brief introduction regarding energy methods. In today's short session, I will give the equation for strain energy for various types of loads. Strain energy, basically it is the energy stored. It is the energy stored in a material when it is being elastically deformed. When it is being elastically deformed. For example, if you are having a bar of any cross section subjected to a load F, so it will be getting deformed by an amount, maybe an amount of delta. So we are going to see the equation for strain energy for a load which is gradually applied. We are going to see the equation for a gradually applied loading case. The other being, in addition to this, the other types of loads can be sudden loads as well as impact loads. But our aim is in the derivation of gradually applied load. So in this derivation, we will be considering a linear elastic material. So if we plot the force extension curve for a linear elastic material, you can see a straight line. The variation will be in the form of a straight line. And strain energy is actually the area under the force extension curve. Strain energy is actually the area under the force extension curve, that is this area. So this area is the strain energy, which is normally represented by the capital notation U. So U represent strain energy, which is the area under the force extension curve. So how will you get the equation for strain energy from this figure? So let me say that this load, let the load be P, and the corresponding extension is delta. Let the load be P and corresponding extension is delta. At any intermediate location, at any intermediate point, so let the load be F and the corresponding displacement, let it be X. That is, when the load is zero, deflection is zero. When the load is P, the deflection is equal to delta itself. So how will you get the area under this curve? For that purpose, what I am going to do is, I will be taking a small strip here. And let the width of the strip be dx. So if you, what you can do is, in order to find this area under this curve, you can have the summation of these elementary strips. The limit varying from 0 to delta. So the strain energy U is equal to integral from the limit 0 to delta area of the strip. Area of the strip is F dx. Area of the strip is F dx. And based on the figure, we can see that based on this particular condition, we can say F by X equal to P by delta. So F is equal to Px by delta. So when you integrate, U is equal to 0 to delta. Instead of x, I will be writing Px by delta dx. That is P by delta x square by 2, the limits 0 to delta, which will give U is equal to half P delta. So this is the equation for strain energy for a gradually applied load. So you can see the load is a function of, strain energy is a function of load as well as the corresponding deflection. And if you plot the area, if you see the area with respect to the y-axis, and this particular region, it is called U star, and which is called complementary strain energy. Is called complementary strain energy. So even though this is the relation which we see, U is equal to half P delta, more often we will be making use of equations of strain energy using material properties, load geometry, etc. So that we can see. So here the load